We're going to be talking about what muscles do and what they don't do, some of the facts and fallacies of muscle behavior, trying to throw away some old models of dead guy anatomy, levers and pulleys, everything stuck into 3 cardinal planes, and why the sliding filament theory is a lie. All of that and more.
It's not a total lie.
All of that and more on this week's episode.
Welcome to Reconsider. I'm Bill Hartman. This is the podcast to challenge you to ask better questions, to look beyond traditional models of thinking and arrive at better health and fitness solutions.
Well, you gotta say stuff like that in the beginning, otherwise people.
Yeah, but it's not a total lie.
Everything you've been taught about muscles has been a lie.
No, it's just limited. It's just too small. That's the problem.
People that we work with, people trying to learn the UHPC model. We talk to people who don't really know anything about anatomy, or they haven't looked at an anatomy textbook or thought about the anatomy that they learned in school for 15 years.
Or thought about it differently. That would be
thought about it differently.
I would look at that.
But I think a lot of times you might reference a muscle or an attachment site of a muscle, and people look at you like they're just, like a dog like one of our dogs trying to figure out what's going on. The head tilt.
Yes.
So in order to help with that, Bill has been starting to put together this tandem 2-part course on the UHP network about behavioral anatomy and propulsive anatomy, and understanding from the perspective of movement as a behavioral thing, this emergent behavioral thing, not dead guy anatomy that's typically taught in school, not really static representations that don't really have water really in the system anymore. Things that work like levers and pulleys in 3 planes of motion versus something that's 4-dimensional that involves helical motion and twisting and turning, as we would come to expect from the perspective of like the UHPC model. So I guess maybe talk a little bit about.
Should we kill the levers and pulleys first?
Yeah, so let's kind of tip some sacred cows over first.
Yeah.
And then talk about why coming up with like this behavioral and propulsive anatomy idea was important.
Yeah. Well, if you look at a cadaver, and especially the kind that we always look at when we're in like PT school or medical school or whatever it might be, they're fixed cadavers, which means they're very dry. Like they're gooey, but they're dry. They don't have the same fluid content as a normal human being does. And I can't think of the name of the study. There was a study in 1980, which is great. It's a great study because they took intact fresh cadaver joints and they tried to approximate the bones, try to get the bones to touch, and they couldn't get them to touch. There was always a fluid space in between them. Then they took a degenerated joint, okay, and they could make that touch. So an intact joint. So even if it's not a living, breathing human being, but if it does have the water in it, like the synovial fluid in it, you cannot get the joints to touch. And so right away, that creates a little bit of a problem from the lever system standpoint, because one of the requirements of a lever is to have a fulcrum. And that means that something has to touch. And if there's no fulcrum, there can't be a lever. And so then we have to say, well, okay, how does this thing work? Well, if it's fluid-based, then it's going to be pressure related. And so what we're going to see is a change in the fluid position within the joint that's going to allow us to change the shape of the joint. And if that's the mechanism, then we have to start looking at everything a whole lot differently as far as its regulation of the fluid dynamics and the way that we use pressure, because that's essentially how we move. We use energy to change shape to move. So what we're looking at when we're seeing what we would reference as a joint movement, it's literally just a shape change that's associated with a big bag of water that can change its shape. That would be a muscle. It's attached to connective tissue, which would be connected to other connective tissue. And so then we have this fluid-based pressure system that allows things to change shape and move. And then if we understand that, then we have to say, well, okay, so all of these references to how muscles behaved are not accurate enough as a descriptor of living, breathing human movement. Like if we look at a cadaver, I can pull on a hamstring and I can make the knee bend, right? And that literally looks like a lever and pulley system in a cadaver. But as we move through space, it's like, okay, that becomes a very limiting perspective as to what these structures are actually doing as far as resolving movement.
Yeah, and I think if someone can appreciate how a foot moves as someone's walking, they can start to see how it's not there's no hinges and bends to joints like typical levers you would see. So,
Yeah.
and what I'm referring to is, just the pronation and supination that someone might see at the foot. That, I guess, if you look at that, you can appreciate that the foot is internally rotating and externally rotating as it's pushing through the ground.
Yes.
So in a structure that was very based in frontal, sagittal, and transverse plane, you would not see that sort of flow from the rear foot to the forefoot of supination to pronation or turning into the ground.
Yeah. You can even fall back on the traditional axes of the rear foot, and you can see that none of them are straight plane. Right?
Yeah.
So they're all resolved. They're all resolved with turns. So,
right.
so that's what we're doing. So we're turning into the ground, and then we're projecting away from the ground.
So right? if we're taking that. So we talk about iteration, we talk about fractals, and we take that sort of twisting, turning, helical motion behavior.
Yes.
You can see that in other parts in the body too.
Oh yeah.
Maybe we can make a couple examples of maybe that happening at the knee or the pelvis.
Sure.
And then we can relate that to the structure of the foot, how it moves, and then maybe like a particular muscle, like gastroc soleus Achilles, maybe.
Yeah, just take the foot as it makes ground contact, and you could read any reference to walking that would describe this. It's like we're gonna make our initial contact in this externally rotated position. As I move my mass up and over the foot has to be able to turn towards the ground. And so people will recognize this as a reduction in the height of the arch. But what it is, it's the internal rotation that's propagating from rear foot towards the midfoot or through the midfoot. Right. So that's a turn inward, but that's also associated with a turn in the tibia. Right. And the tibia is the lower part of the knee. And so again, I would have relative motions at the knee, then I would have a tibia that would be rotating relative to the femur, right? And these are some of the things that are recognized as being important, because what this does is it allows us to absorb energy in a distributed manner from the ground and reuse that energy, so we can store this as we're moving across the ground. Our center of gravity moves over the foot. We push down into the strongest representation of internal rotation in the ground, and then we project ourselves away from that ground contact, and then we see this reemergence of the external rotation, right? Yeah. Which is the way that we project ourselves. And so everything that we are follows this same strategy. We look at if you look at the sarcomere, at the smallest muscle level, not smallest, but you know what I mean. And we always get that two-dimensional, the interdigitation, two-dimensional representation of the sarcomere. And what you can't appreciate is that those myosin heads that are attaching and releasing from the actin, they're oriented in a helical manner at about a 60-degree angle. Right, so they propagate along the myosin filament 60 degrees apart, but also in this helical orientation. And so we see this twisting and untwisting even at the sarcomeric level, and then we move out farther, and then we see fasciculi doing the exact same thing within the muscle. Right, if we look at the big muscle, we see that all of these muscles are actually twisted as they are attaching to their bony attachments. We see the trabeculae inside the bones. They're also oriented in this same twisting manner. And then we project this out to the macro scale, and we see this twisting inward and outward through the entire system as we move.
Yeah.
So it's the same strategy throughout.
Yeah, it's saying that like the sliding filament theory is a lie is a way to get someone's attention, but so there are parts of it that are true. It's just it's not this flat sheet of tissue that's being pulled towards each other
Right.
by ATP and the myosin heads interacting and grabbing and pulling.
What's the
It's
energetic component of that I would question?
Yeah, so it's
Yeah.
like ATP not really being this like it's not this shuttle of energy necessarily. It's more of like what do they call it, a hydrotrope, where it
Yeah, it carries a
changes.
charge. It's the charge differential that creates the protein shape change. It's not the. It's not
Right,
the. They always say we cleave off a phosphate, and there's a release of energy, and it's like, well, there's a discharge of energy, but it's not the phosphate bond that is the source of it. It is just the differential in the charge of the molecule. So an ATP molecule carries a very strong negative charge. ADP, right? ADP carries a more positive charge. And so when the because of the charge differential, it creates a difference in the shape of the protein. So this is again, it's just another representation of movement via shape change, right?
right.
So
Because
again, it's
it
the same
creates
principle. Yeah,
a gradient of charge, right?
that's correct. And that's how stuff moves back and forth within a cell, and that's how it like. So there's a charge gradient that would take the ADPs back to the mitochondria, and the ATPs are shuttled in the opposite direction.
Yeah.
Just following a charge gradient. Yeah.
So that's it's we create gradients of pressure and volume to
Yes.
get stuff to move throughout the body, but
Yes.
we also the energetic components are of what we're talking about with ADP and ATP and that whole
Mhm.
cycle is
Yes.
creating a charge gradient to
Yes.
change the shape of the
Yes.
protein structures.
Yes.
Right.
Those are called phase transitions, which we also use in terminology associated with locomotion.
Yeah. So
So
it is coherent.
yeah, it's just this consistent representation. It's like we don't have to change the principles, right? We just have to say, okay, so movement is a gradient. Yes, that would be
Yeah.
correct. And that gradient changes the shape, which is what we observe.
Right. So our main contention is that we just don't like structural reductionist representations of anything really, and that's kind of what the sliding filament theory is presented as.
Well, in the end, the way they gloss over it in when I was in school, it was just like a thing, and then you learn
Yeah.
that, and then you don't ever talk about it again.
Well, it's like mitochondria. Everyone learns the mitochondria is the powerhouse of the cell, and then they learn that
Oh, I knew you were gonna.
they learn that
I was waiting. I
they
was
learn
waiting.
that ATP is this magical like power plant.
Yes,
It's this
right
little wheel.
now.
It's this little wheelbarrow that carries around a charge.
Yes,
And it drops it.
there's a young man right now that is vomiting in his mouth, and it's not me this time. It's actually a dear friend of mine, an acquaintance of yours, who works at the professional sports level. That we have a running gag that everybody has to say that.
Yeah,
It's like the
important.
unwritten rule.
Well, it's funny too. Everyone knows that. It's you could ask anybody what mitochondria
On the street.
is.
Yeah.
On
What's
the street.
mitochondria?
They
Oh,
would
it's
be
a
like,
powerhouse of the cell.
powerhouse of the cell. I don't know. That's the greatest. I don't know, textbook definition that was just plastered in everyone's biology class.
See, I think
in high
that's
school.
a little bit of a misrepresentation, but we don't want to get distracted.
Yeah,
we'll,
I mean that's
we'll stay focused.
right.
The
Okay,
point being,
so
let's get back to muscles. Let's get back to the big representation. The point being is that when we're looking at cellular mechanisms of shape change, we don't, like I said, we don't have to change the principles. We look at this thing from this macro perspective, and the muscles behave the same way, but it creates some really cool behaviors within the muscles themselves. So you go back to the traditional frame of reference of origins and insertions and the way that muscles will behave. It's like I pull on something proximally and the distal segment moves, and that's how most of the muscles were sort of determined as to their behaviors, without the consequence of like, oh, it could go the other way. Literally could go the other way. So to give you a perspective. So if you look at flexor hallucis longus muscle is an easy one, I think, to see, because you just look at the end of the toe bending, right? So flexor hallucis longus means the big toe bender, literally by translation. So it's a big toe bender. It'd be this big toe bender. But what you got to appreciate though is like if you're walking across the ground, it's helping to bring the heel back off the ground, right? It's actually one of the mechanisms that produces this reemergence of external rotation as we're propelling through middle into late propulsion. And so if that would have been the perspective, looking at it from a dynamic, living, breathing human being, maybe it should have a different name versus, again, the big toe bender, right? You look at glute max, right? So glute max is about 7 different muscles if you look at the way that it is actually attached to the remainder of the system. But you could just look at the deeper portion at the most inferior aspect. It actually is it's a pressure container, and then you look at the superficial element of it, literally right on top of it, and you have something that is a very strong projector of our center of gravity forward. So literally by name, it's the same muscle. By behavior, 2 very distinct behaviors, that makes anatomy exceptionally cool versus just saying that, the glute max, I'm going to throw up a little bit, extends the hip and externally rotates the femur, right? And that doesn't give us the nuance of behavior that makes the anatomy so elegant in the way that it behaves.
Yeah, I think if you were to, maybe if you took the perspective of like, if I start on a muscle fiber of like the gastroc or the soleus, and I was to drive along it like on a car,
yeah,
where you would end up once you got to the calcaneus, you would be taking this like real spiral sort of path all the way through, like, and it would rotate and twist.
The Achilles tendon itself twists 90 degrees prior to its attachment.
Yeah.
Right. I mean, that's a big twist, but a tremendous energy saver. Like if it didn't do that, and this might be one of those reasons behind why, as people tear their Achilles and they get the repair done, and we see deficits in performance that are associated with that, and they're being multifactorial. I'm not weighting it as the absolute, but as a contributor, it's like if I don't have that same capacity to produce the twisting and the untwisting, it's like, okay, I don't store energy as efficiently as I did before, and I certainly don't project it as well as I did before. So, just a consequence of the change in structure. But this is also one of those things that we're going to see in people that have rear foot adaptations. It's like, oh, you're a great energy absorber, but you can't release it to save your life, or vice versa. It's like if we had to worry about just releasing energy, you're in a perfect position, but you can't absorb it, right? And then you're going to have to construe some way to produce those behaviors, which is resulting in compensatory activities and so on and so forth. Right. So this gets really interesting when you start looking at how this stuff really behaves, which is why it's important to, and I always tell people try to speak both languages kind of a thing. It's like understand what the traditional, references provide, but don't blindly accept that as the absolute, because there's so much more information that's available to us that doesn't get applied effectively. Right, because people accept the simplest of definitions because it's easy. Like gaining the nuance is hard, and you'll still be wrong sometimes. But it's certainly, like I said, it's much more interesting to look at this thing from the behavioral perspective.
Yeah. So if this is an interesting topic for people, like over the course of the next year or so, Bill has been putting together these behavioral and propulsive anatomy lessons, and those will be on UHP Plus. And you'll be able to go in there and check it out. It comes with your UHP Plus subscription, so that's a cool sort of added benefit of that. But yeah, it is an interesting thing to think about, and it kind of helps you understand why people talk about the actions of muscles being different at various levels of a squat, for instance. It's like what the deep 6 rotators do at the bottom of a squat is actually different than what they do when you're standing upright. And it makes a lot of sense when you look at it from the perspective that you're saying, where it's like as the bones are changing shape, as I move through these propulsive phases, the actions of that tissue are going to have to change as well, just because of
Correct.
what ranges of motion and space you need to be able to acquire, and then how the shape of the muscles has to change to kind of push you through that space,
Right.
to move through that space.
Yes, the shape of the muscle and then the shape of the entire system is what determines what the movement outcome is going to be.
Right, because you got that sort of imagining like an amoeba projecting itself through the water, where it gets big, it shrinks, and then it gets big again to sort of move itself through space
by direction as well.
Yeah.
So it changes shape in the direction that it is intending, whatever its intention might be. As an amoeba, I don't know how deep its thinking processes are.
You take that, you put it in a less viscous field of air that we experience. You put it on two legs with strong gravitational force underneath it. You give it bony constraints, and then you just amoeba your way through space.
That's it.
Yeah, it's really we're just worms with like some bony constraints that are trying to not fall on our faces.
Even those change roles,
right?
You know, so but that's a different topic.
Yeah. Okay. What was the we talked about
pizza last time?
We talked about shoes. We talked about like, do you remember like what were like the coolest shoes when you were a kid? Like what kind of shoes did
I know exactly
want?
What this is. I know that. Okay. Got to tell you a quick story. B&K Sporting Goods had a sale. Here you go. $6. $6 for a pair of high top Chuck Taylors of various colors.
Nice.
$5 for a pair of low cuts. Holy cow. So these two big giant bins, like big ones, like mail, the post office bins where they're pushing volumes of mail, right? Huge, full of shoes. You go in there, you pay your $6, and you got to hunt through and you got to sort. And so everybody's walking around in my hometown with black ones and green ones and blue ones and red ones and the traditional white. It was awesome. It was an awesome summer because it happened like at the beginning of the summer and everybody had Chuck Taylors. Best shoe ever.
Yeah. Such a simple concept for a shoe.
Great
middle piece shoe.
It's like that's why the powerlifters like it so much, right?
Yeah,
because
makes sense.
That's why they promote it, because it is the strongest representation of a forceful foot in that circumstance. Absolutely. Yeah. And then it's canvas, so it's constrained, which is just great.
Right. But it still has some motion to it, right? Like canvas is not. It's like it still has some elasticity to it.
Well, it doesn't stretch, right? But it does have an element of give that allows you to acquire the foot shoe.
Well, that's someone
flat.
wearing.
But it's as flat a shoe as flat
powerlifting gear, like the denim powerlifting jackets and stuff, give you a little bit of spring. So
exactly.
For us, it was like when I was really little, it was still the time of the pump shoes with the air bubble.
Yeah,
you could get a little support from that, and then there was the I think when I got a little older, middle school and high school, everyone was wearing those like either shoes that had plastic plates on the midsole, so you could like grind down railings and stairs and stuff, because that was when like rollerblading was really cool. So they just made shoes that had little grind plates on them, and then also like they had the shoes where they put. These still exist. I don't think I've seen them as much as I used to, but they put a wheel in the heel.
Oh yeah,
so you could run really fast, and you pull your toes off the ground, and you could ride on your heels.
The wheel. Nice.
Yeah. Those were always cool.
That's after my time.
And then light up shoes. My son's got all sorts of light up shoes.
Those are awesome.
The shoes that Bill and I have been testing are like really bright colors, and he thought they had lights, so he was like, he took them, he was like hitting them on the ground. He's like, do these light up?
That's awesome.
Yeah, because why would you not have lights in your shoes? It's a very good question.
Our friend Dale's going to talk about PF Flyers without a question in my mind.
That's from Sandlot. Yeah, they talk. The PF Flyers is in Sandlot.